Hey, good people. Arthur Morris here. Hope all is well. In this video, we're going to look at optimization problems. So you may want to pause the video here and write down these steps. All right, so step one, we're going to determine the equation to be optimized, maximum or minimum. Uh, then we're going to determine the secondary equation. We're going to isolate one of the variables in the secondary equation, substitute the result from step three into the optimized equation, apply the first and second derivative tests. Okay. All right, so with this first problem, we have the sum of s, some number s is equal, and the product is a maximum. We want to find two positive numbers that satisfy the given requirements. So let's let the first number be called x, and let's let the second number be called y, and then we'll call the product p. All right, so the optimized part comes where you see the maximum or minimum, so the product is being optimized. So step one, we're going to have p equals x times y, the product of the two numbers. That's the optimized equation. The secondary equation would be the other equation, which in this case is the sum. All right, so the sum, we're looking at that number as being a constant number. So we want to, step three, isolate one of the variables in the secondary equation. So I'm going to subtract y from both sides. And then step four, we want to use substitution and go back to the optimized equation. So this, I'm going to replace x with s minus y. And then we want to simplify this, and then we'll find our first derivative. So remember, s is a constant in this case. It's a constant number. So in this case, it'll be a constant multiple. All right, step five, let's find the first derivative of the product equation that we have here. So since s is treated as a constant number, then I have 1 times s, which is s, subtract 1 from the y, that goes away, so minus 2y, first derivative with respect to y. And I like to go ahead and find my second derivative as well here before I set it equal to 0, just out of preference. So the second derivative, the derivative of a constant is 0, so the derivative of negative 2y equals negative 2, which we know is less than 0, and if that's less than 0, the second derivative is less than 0, that means that this thing is concave downward, which means the numbers that we come up with will be a maximum. Okay, so let's go ahead and go through our first derivative. Let's set it equal to 0. Solve for y, so we need x and y are the numbers that we're looking for. So divide both sides by negative 2, and we end up with y equals s over 2, or 1/2 s. All right, but we need x and y. We need both of the numbers. So the second number, we saw back in step 3 that x was equal to s minus y. So since x is equal to s minus y, I can come out here and replace y with s over 2, or 1/2 s. So we have 1s minus 1/2 of s. And 1 minus 1/2 is 1/2. So that gives us the same thing, 1/2 s, or s over 2. And those are the two numbers that are in this, given this situation, the product of those two numbers will be a maximum where those sum of the two numbers equals s. All right. All right, so this one we're looking for the product of two numbers that's 185 where the sum is a minimum. And we're still looking for two positive numbers, okay, per the directions, previous directions. So we're still looking for two positive numbers. All right, so the sum is a minimum. That is what is being optimized. It's the sum. So we want the product of two numbers that has a product of 185, where the sum is the smallest amount we can get with that with those two numbers giving us the product of 185. All right, so let's start off step one. Let's identify or define our variables. So we'll let the first number, again, we'll let it equal x. You can call it whatever you want to call it. Second number, I'm going to let it equal y. And then the product we know is equal to 185. So sum, we need a variable for that. So I'll call it s. All right, so step one, the optimized equation, the sum of the two numbers is a minimum. So s equals x plus y. And then step two, our secondary equation will be the other equation, which is the product in this case. It says the product equals 185. The product of the two numbers equals 185. All right, same thing. Step three, we want to solve for one of those variables. So I'm going to divide both sides by y. And then step four, we want to come back and use substitution. So I'm going to replace x in my secondary equation with 185 over y plus y. All right, so we can write that since we're getting ready to take the first derivative, we can write that as such, 185 times y to the negative first plus y. So step five will be to take the first derivative of this. So multiply by negative 1, that gives us negative 185. Subtract 1 from the exponent, that's negative 2. Multiply by 1, subtract 1, so that's plus 1. The derivative of y is just 1. All right, let's see, and from here, let's go ahead and find our second derivative. So negative 2 times negative 185 is 370. Y to the negative third. Okay, and derivative of 1 is 0. So we have the second derivative, 370 over y to the third. And for this to be a minimum, we know that this must be greater than 0, which it will because we're looking for two positive numbers. And if I replace y with positive numbers, then it will remain positive. The second derivative will remain positive, which will be greater than 0. If it's greater than 0, then it's concave upward. And if it's concave upwards, then we have a minimum there. Okay. All right, so that's taken care of. That check is taken care of. Let's come back over here to our first derivative. Let's rewrite it. And then let's set it equal to 0 to find the value of y. Okay, so we can multiply both sides by y squared. So using my distributive property, y squared times negative 185 over y squared is just negative 185. And then y squared times 1 is y squared. Y squared times 0 is 0. All right, add 185 to both sides. Find the square root, keeping in mind that we're looking for two positive numbers, so we don't have to worry about the negative case here. So if I take the square root of both sides, I get the square root of 185 for y. So that's one of my numbers. We have to find two numbers. The other number, remember, is going to come from the equation from step 3 there, where we have x equals 185 over y. So let's move out here, and x equals 185. We know that y is the square root of 185. All right, and then let's get that square root out of our denominator. So we get 185 times the square root of 185 all over. When we multiply the square root of 185 times the square root of 185, that's just 185. And then finally, those cancel. So x also equals the square root of 185. Now that won't always be the case. Those two numbers won't always be the same, x and y, but they are in this case. So it says the product of those two numbers, the product of these two numbers, that gives us 185. Those are the smallest they will also give us the smallest minimum sum when added together. Alrighty, let's see what we have here. Next up, we want the sum of the first number and twice the second number is 108, and the product is a maximum. So we see that the product here is what is being optimized. So let's define our variables. First number, we'll call it x. Second number, we'll call it y. And then product, we'll call it p. All right, so the sum of the first number, so let's optimize equation first. The product is a maximum, so p equals x times y. And then the sum of the first number plus twice the second number equals 108. All right, so we have our optimized equation and our secondary equation. Now let's isolate a variable in our secondary equation. So I'm going to subtract 2y from both sides. And then I'm going to use substitution back into the optimized equation. So I'm going to replace x. And let's use distributive property here to clear those parentheses. So 108 minus y times y minus 2y to the second power. Okay, let's find our first derivative. Let's go ahead and find our second derivative, and we're still looking for two positive numbers in this exercise. So second derivative is -4, which is less than 0. And since -4 is less than 0, we know that this thing is concave downward, which will give us a maximum at whatever point that we find. That'll give us a maximum. All right, so let's go back over here. We got that checked out. Let's go back over here and set our first derivative equal to 0 and solve for y to find the y coordinate of that point. So subtract 108, divide by -4, and that gives us 27. All right. Again, we want to use the equation that we found in step 3 to find the value of x. So x equals 108 minus 2 times y, or 2 times 27 in this case. So x equals 54. So the two numbers that fit the conditions that we had in our instructions will be 27 and 54. All right, all right, all right. Let's look at one more problem here. Okay, so in this problem, we have a farmer that plans to fence a rectangular pasture adjacent to a river. So you see the river up top. The pasture must contain 245,000 square meters. So the area on the inside should be 245,000 square meters in order to provide enough grass for the herd. No fencing is allowed needed along the river. So we'll call the outside, we'll call it the perimeter. It's not the true perimeter since we don't have to count the top part for the river, but we want, it says what dimensions will require the least amount of fencing. So we want our perimeter to be a minimum. The y here on the left, the x on the bottom side, and the y here on the right. We want the least amount of fencing possible. So we want that perimeter to be a minimum. So we have the x and the y, and we know that the x times the y should equal 245,000 square meters. And we also know that the perimeter, based on the diagram, we have two y's and an x. So that fencing adds up to be x plus 2y. Okay, so let's go back in the order that we've been doing this in. So let's start off by writing our optimize equation. So the optimized equation is the perimeter, and we'll just call it sum. Let's say the sum. So let's let S equal sum, and the sum of those sides. So sum equals S. So the sum of those sides is x plus 2y. So S equals x plus 2 times y. And then our secondary equation is the area, or the product. The area should equal 245,000. Okay, so we have our optimized equation, we have our secondary equation. Once we have that, we just go through the steps. Isolate one of the variables in the secondary equation. So I'll divide both sides by y. And then use substitution. So come back to your optimized equation, replace x with the 245,000 divided by y. And next we want to find our derivative. So let's move that y to the numerator. Make it y to the negative first. And then let's find the first derivative here. So negative 245,000 times y, subtract 1 from that to the negative second, plus 2. And we know our dimensions have to be, our x and y must be positive because we're measuring. Let's go ahead and check our second derivative while we're at this point. Second derivative, negative 500,000, negative 490,000, sorry. And that should be positive because we have a negative exponent and multiplying negative exponent, and we're multiplying times this negative out here. So positive 490,000 y to the negative third. And since we know that y must be positive, then if a positive divided by a positive is going to continue to be positive, so we know that's greater than 0, which means that this is concave upward, which means the point that we find when we set our first derivative equal to 0 will be a minimum. Okay. All right, so let's see here. Let's set our first derivative equal to 0. I'll move this y back down to our denominator. So negative 245,000 divided by y squared plus 2 equals 0. Then we want to clear the y square, so let's multiply both of the sides of the equation by y squared. We want to clear that denominator. So distributive property here, it gives us negative 245,000 I plus 2y squared equals 0. And then solve for y. So add 245,000 to both sides. And then divide by 2. And then the square root of each side. And remember, this must remain positive. So y is equal to 350 meters. But keep in mind, we need x and y, the dimensions. So we need to come back up here and find x. From step 3, we know that x is equal to 245,000 divided by, in this case, 350. So x is equal to 700 meters. And that's how you use those the steps to solve those optimization problems. Alrighty, good people. I hope you found this video to be helpful, and I will see you on the next one. Thank you.